Hello, I'm Stefan, and today I'm going to be talking about relating semi-algebraic proofs and various forms of geometric methods of computation. This is joint work with Mika, Göös, Noah Fleming, and Robere. So let's get started with extension complexity. So the concept here is if you have a polytope in lower dimensions with a set number of facets, it might be easier to have a higher dimensional polytope with fewer defining facets that projects down to it. So for example, in this image here, we have a lower dimensional polytope P with 8 facets, whereas there's a higher dimensional polytope P prime that projects down to it linearly, which has a smaller set of descriptive inequalities. And so why might this be an interesting concept? Well, it is useful for speeding up linear programming. If you were to optimize over P, this would take longer than optimizing over P prime and then projecting downwards. Now, this whole concept came about in the 1980s when Yannakakis was trying to solve the problem of refuting increasingly esoteric linear programs that people were conjuring to prove that P equals NP. So he wanted to prove that, say, the traveling salesman polytope had exponential extension complexity, thereby automatically refuting any and all linear programs that people might come up with. So we're going to be studying extended formulations and complexity for pairs of polytopes. So let P and Q be 2 polytopes where P is contained in Q. And an extended formulation K of this pair is a polytope that lives in higher dimensions and projects in between the two. So in this picture here, we have P, the inner polytope, Q, the outer polytope, and K, which projects downwards in between the two, so containing P and a subset of Q. And we can formally define extension complexity as minimizing over every extended formulation of the pair PQ on the number of defining inequalities. And so this is an interesting concept. However, it's difficult to work with just this minimization. So we would like a more concrete way to handle extension complexity, a combinatorial representation. So in order to do that, I need to define a matrix, the slack matrix, where for, again, our 2 polytopes P and Q, P contained in Q, we'll have the vertices of P, V1 through Vn, and the defining facets of Q, A1 x less than or equal to B1 up to AM x less than or equal to BM. And from this, we get this slack matrix, which is a non-negative matrix that contains as elements the distances from the vertices of P to the facets of Q. And so a beautiful theorem from Yannakakis in 1988 is that the non-negative rank of the slack matrix is in fact equivalent and completely encapsulates extension complexity. So our goal is going to be understanding extension complexity as actually a circuit model for computing Boolean functions. Yannakakis did this briefly in the original paper by showing that you can simulate Boolean gates by inequalities. So for example, we see here we can convert a NOT gate to a single inequality, as well as OR and AND gates to a sequence of inequalities, giving us that if we have a Boolean circuit of size S, we can get an extended formulation as well of big O of S. So let's actually dive into a model of computation. And for that, we need a separating polytope. So for a Boolean function F, a separating polytope P of F is a polytope that contains the convex hull of the ones and has an empty intersection with the zeros. Now, this was first loosely considered by Yannakakis and then was more formally defined by Robere. So here is just a pictorial description of a separating polytope. Inside, we have the convex hull of the ones of F, P, which contains this convex hull and has an empty intersection with the zeros of F. Now, as well, we can define a separating polytope for monotone Boolean functions, and it would look something like this. However, it takes a bit of technicality to fully define, so I will leave that. All right, let's jump into an actual non-uniform model of computation, and this was introduced by Robere in 2012. And to do that, we're going to be taking use of the extension complexity. So we're going to want an extended formulation that as a separating polytope. And in order to do that, we need an outer polytope. We have an inner polytope of the convex hull of the ones of F, and we need an outer polytope. And we define an example of an outer polytope here. And we'll do this using Hartman-Wigderson inequalities. So let's define this polytope QF1, where we define an inequality for every 0 of F of this sum from I1 to n of xi by 1 minus yi plus 1 minus xi by yi is at least 1. Now, on the left-hand side, this is actually equivalent to the Hamming distance between two Boolean strings, x and y. And on the right-hand side, we have at least 1, because any 1 of f is going to have at least Hamming distance 1 between any 0 of f. So pictorially, we see this below. We have the convex hull of the ones, and the inequalities of QF1 are fleshed right up against the convex hull. So again, we can actually do this for monotone Boolean functions. And here we can just drop the latter part of the sum here because we know that f is monotone. Now, since all we care about is a separating polytope between the ones and the zeros, we actually don't necessarily need a 1, as in QF1. We can do it for any positive epsilon. And so when you do that, we get this new outer polytope QF epsilon, where instead of having a 1 over here on the right-hand side of the inequality, we have an epsilon. And pictorially below, we see that this gives more space than QF1 had. So potentially you could have a smaller extension complexity of some polytope that lies between the convex hull of the ones and QF epsilon than you might have with QF1. And so we can see that here with QF1 being right up against convex hull and QF epsilon giving more breathing room. So we can, as Robere did, define formal complexity measures here with separation complexity. So on the left-hand side, we have sep1 of F, this being the non-negative rank of the slack matrix -1, and we have a monotone version as well. And on the right-hand side, we have separation complexity of F being the minimization overall epsilon larger than 0 of the non-negative rank of the slack matrix minus epsilon, and likewise a monotone version. And we minimize epsilon here just so we can find truly the best extended formulation we have as a separating polytope between the ones and the zeros. And a nice property here, as Robere proved, is that these complexity measures are not that esoteric. In fact, sep1 lower bounds formula size and separation complexity lower bounds circuit size. And just to nail it in, by Yanikakis's factorization theorem, the nice way to write separation complexity would also be minimizing our epsilon of the extension complexity of this pair, the convex hull of the ones and QF epsilon. So now we would like to analyze query and proof complexity versions of this exact analysis. So let's start off with our first semi-algebraic proof system, conical Hunter degree. And all we're going to be doing here is introducing a way to give a certificate that a polynomial is non-negative. So we'll work over variables x1 through xn, and let's take S a subset of the indices 1 through n, and T a subset of the complement. Then a junta is just going to be a product that represents a conjunction. So what do I mean by that? If we have a conjunction here, x1 and not x2 and x3 and x4, well, this would give the corresponding junta, where we take all the positive variables in the conjunction and multiply it positively here. And then we take the negative variable, which is x2, and multiply it as 1 minus that variable here. Now, conical junta is just going to be a conical sum of juntas. So what that is just taking non-negative coefficients and multiplying them to juntas and making a sum. So now we can actually make a complexity measure out of this. We can call it conical junta degree as deg plus, and this will be the minimal degree such that we have a conical junta representation of F. And as a reminder, if we have such a representation of F, then this is a certificate that F is non-negative. Now, we actually kind of seeing this already, where for extension complexity, a slack matrix is non-negative, and making that factorization of the slack matrix into a sum of non-negative rank 1 matrices is a proof of that non-negativity. And we're actually going to do the same thing here, but for a polynomial. And we're going to show it's non-negative by factoring into a sum of juntas. So what is that polynomial going to be? It's going to be the number of violations. So if we have C to be an unsatisfiable CNF, then we define this polynomial here, the violations of C, to be the sum over the negations of the clauses. And on an input, this is going to count the number of violated clauses. Now, if we can show that this polynomial is non-negative, specifically greater than 0, then that means we've proven that our CNF is unsatisfiable. So we would like to prove that vial of C minus epsilon is larger or equal to 0 for some epsilon, this giving a certificate that the CNF is unsatisfiable. Okay, so if we do a Robere style minimization, as we saw for separation complexity, for conical junta degree, perhaps this is interesting to examine. And it turns out that this is equal to something quite natural. It is equal to Shirali-Adams degree. So Shirali-Adams is another proof system, a generalization of conical junta degree. Again, it's a certificate that the CNF is unsatisfiable. And really what's going on underneath is you can think of it also as a hierarchy of polytopes that converges to an empty integral hull for an unsatisfiable CNF. And this proof system is also well studied as an analysis for using linear programming to give as an approximation algorithm. So let's actually see a Shirali-Adams refutation. So what that is given a CNF C. A refutation is a list of conical juntas J1 through Jm plus 1, where on the left-hand side, we have the negated clauses with a -1 multiplied by these conical juntas, plus an additional conical junta here equals -1. And why this is a refutation is because the left-hand side is non-negative, whereas the right-hand side is -1. So we can define, again, a complexity measure here, Shirali-Adams degree, as the minimal degree D appearing for any Shirali-Adams refutation of C. And we can also define size as the minimal number of monomials we need for a Shirali-Adams refutation of C before cancellation. And if you'd like to see more specifically on lower bounds or other semi-algebraic proof systems, I recommend seeing Noah Fleming's survey on Shirali-Adams and other semi-algebraic proof systems. So our results, well, we already saw that this Robere-like minimization of conical junta degree on the violations is equivalent to Shirali-Adams degree. So we can also ask, well, if we have conical junta degree of vial -1, does this actually differ from minimizing vial minus epsilon? So we know that at least it is simulated by, but can the simulation go the other way? And we answer to that negatively. We show that there is a family of formulas that resolution can easily prove, whereas it cannot be done in low degree for conical junta degree. So more specifically, the conical junta degree of the violations of this iteration family, -1, is at least linear. And iteration here is just an unsatisfiable family of CNFs representing the house sitting principle. Okay, so likewise, we can use lifting to apply all of this to circuit complexity classes, specifically separation complexity. And we're able to separate monotone circuit complexity from MSEP1. This again shows that MSEP is strictly stronger than MSEP1. And the way we do this is we use KMR lifting. Kothari, Mika, Raghavendra showed that you are able to lift conical junta degree to non-negative rank. And so that we are able to take our results for Shirali-Adams degree and lift it to separation complexity. So here are all results in one picture. We have our separations and lifting. And we also showed feasible interpolation. meaning that we can take the proof system, we can take a refutation, a Shirley-Adams refutation, and convert it into a computational model that simulates it. So we have a simulation of Shirley-Adams degree by monotone separation complexity. And this was first examined by Hakoniemi, but his feasible interpolation was slightly different, where he feasibly interpolated Shirley-Adams by a proof search algorithm rather than monotone separation complexity. Okay, so let's actually dive into one of our results, namely the classification theorem. So we want to show that Shirley-Adams degree is equivalent to this minimization. So let's first look at a near proof of this result in this lemma here. So if you were to have a CNF on M clauses and N variables, and if we were to have a very special Shirley-Adams refutation, namely that the negated clauses are not multiplied by anything other than real coefficients, if we were to have such a Shirley-Adams refutation of degree D and size S, as well as bounded coefficients, 1 over epsilon at most, then this means that we also get the violations of C minus epsilon is a conical junta. Specifically, this conical junta will also have degree D, so no blow up on degree, and multiplied by 2 for size. So this is nearly what we want, except in general, a Shirley-Adams refutation is going to multiply our clauses, our negated clauses, by conical juntas. So somehow in our main proof, we're going to have to get rid of those. All right, so that's exactly what we're going to do. So let's start with a normal Shirley-Adams refutation, degree D and size S, and we're going to expand the conical juntas into monomials. So when you expand, it'll look exactly like this, where the alpha k's are real coefficients, and we have our negated clauses, sometimes appearing more than once, and we have monomials mk. And it will have, in addition, a conical junta added to the side, equaling -1. And so we'll need a brief fact that if you were to sum over all of these conical juntas, summing over specifically over subsets of the indices 1 through n of the junta of S and the complement, then this in fact equals 1. And this is a very simple proof by induction. So given that fact, let's run through an example to see how this proof will work. And we'll use the monomial mu being just the product of xi's from indices 1 through L. And notice that this is actually equivalent to this junta here, where we have 1 through L multiplied positively and no variables multiplied negatively. Okay, so if we were to reverse engineer what we need, then we would start with minus a negated clause. So of course, this equals minus the negated clause times 1. And by our fact, we can expand out the 1 to be minus our negated clause times this sum. And so the first part of the sum is just mu, as we noticed above. And on the second part of the sum, we have a conical junta. So writing this down below, we have minus ci bar times mu minus ci bar times the conical junta. And because ci bar itself is a conjunction, this actually makes this entire thing a conical junta. So if we were to try and get rid of mu, then we're able to do that just by dragging this conical junta out into the conical junta portion of our proof. And so all you need to do to finish this theorem is to repeat this for every single monomial. And what we'll get as a result is a degree D size S to the 2 to the D times 2 to the D conical junta. And if we apply the lemma we had earlier, then this is all we need to finish our proof. So just to summarize everything we've seen so far, we gave a Hrubesch-like analysis of semi-algebraic proof systems where we did a minimization and saw what that equaled. In fact, if you did this minimization of conical junta degree, this gets you Shirley-Adams degree. And interestingly, the epsilon we saw for that minimization corresponds to coefficient size. As well, we separated conical junta degree from Shirley-Adams degree. And we also separated MSEP1 with MSEP by lifting. And I briefly mentioned as well that we feasibly interpolated Shirley-Adams degree by monotone separation complexity. I'd also like to note that all of the arguments we saw for the characterization and feasible interpolation, those also work for sums of squares. So there are some open problems that are very interesting after this work. So the main thing is we would very much like to improve the Kothari-Meka-Raghavendra lifting that we need of conical hunted degree to non-negative rank. And the reason being is if you actually write out the lifting theorem, you have this very pesky 1/100n that appears. And so the problem with this is that we want to show equivalence of these complexity measures, but we can't. At least we need a sufficiently large epsilon to do so. So it would be very nice to get rid of this 1/100n in the proof of this lifting theorem. So next, we have another open problem on some objects I didn't define so far. We would like to separate weak MLP gates from strong MLP gates. Now, what are these? Well, in Oliveira and Pudlak, they defined circuits with gates defined by monotone linear programs. And they showed that, well, there are these two different kinds of gates, weak meaning that your input will only affect one of the objective function or the defining inequalities, and strong, your input will affect both. They showed that a single weak gate is equivalent to monotone separation complexity, and a circuit of strong gates actually feasibly interpolates Lovest-Shriver. And so, this separation between weak and strong gates is quite interesting, especially since we've shown in this paper that weak MLP gates, in fact, interpolate Shirley-Adams degree. Well, thank you for listening.